Okay, in this video we're going to talk about section 5.3 dealing with the Fundamental Theorem of Calculus. And out of that section we're going to be evaluating the area functions and also evaluate derivatives of definite integrals and also evaluate definite integrals using the Fundamental Theorem of Calculus. Alright, so we'll start off with area functions here. The concept of an area function is crucial to the discussion about the connection between derivatives and integrals. And here we're going to start with a continuous function, y equal f of x, defined for t equaling to a. So this is y equal f of t, and t is equaling to a, where a is a fixed number. The area function for f with left endpoint a is denoted by capital A of x. And it gives the net area of the region bounded by the graph of f and the t-axis between a and x, as you can see here in this figure here. So here we're going to be looking for a of x, which is the area bounded by the graph of the function f and the x-axis and the t-axis in this case between those 2 points, t equals a and t is equal to x. Now the net area of this region is also given by this definite integral. A of x is equal to the integral from a to x of f of t dt. So you can see here the x is the independent variable of the area function. And also your t is going to be your variable of integration, or sometimes it's called the dummy variable. All right. So here's the definition of the area function. If I let f be a continuous function for t greater than or equal to a, the area function for f with left endpoint a would be this. A of x is equal to the integral from a to x of f of t dt, where x is going to be some value greater than or equal to a. And the area function gives the net area of the region bounded by the graph of f and the t-axis on the interval from a to x. And it's going to be the closed interval. Now let's look at example 1. And it's this. The graph of f is shown in the figure to the right. And here we're going to let a of x equals to the integral from -2 to x of f of t dt, and capital F of x equals the integral from 4 to x of f of t dt. So here's going to be two area functions that we have here for t. And then we're going to evaluate the following area functions here. So in part A we got capital A of -2. So capital A of -2, that means we need to use this formula for A of x here, which will be the integral from -2 to x, in this case, will be replaced with -2, because that's our x value here, of f of t dt. Well, if you recall, in the last section of section 5.2, when we were talking about the definite integral in general, right here, our upper limit and the lower limits are exactly the same. So the integral from -2 to -2 of f of t dt is 0. Okay. So you might want to refer back to the video for section 5.2 when we were dealing with the definite integral. In part B, we got capital F of 8. So now, capital F of f of 8, we have to use this capital F of x formula here, this function here. That's going to be the integral from 4 to x, which is 8, of f of t dt. and we're going to find this integral from 4 to 8. So here's 4 right here, and here's 8 right here. That's only going to be this area here. And notice that this area is below the x-axis. And anytime you have an area below the x-axis, that means that this area will be negative. And of course, you see that the area for that is 8. So it will be negative 8 since it's below the x-axis. So the integral so capital F of 8 will be the integral from 4 to 8 of f of t dt will be negative 8. Now part C, a of 4. Well, now we use the a of x function here and replace the x with 4, so it will be the integral from negative 2 to x, which is now 4, of f of t dt. So in this case, look at this graph from negative 2 to 4. So here's negative 2 right here, and here's 4 right here. So now we got two areas that we're going to be dealing with. This area that's in blue and this area that's in light green. And that area there is 9, and then we have another area that's going to be 18. And they're both above the x-axis, so they're going to be positive values here. So if we add 9 and 18 together, you'll get 27. So a of 4 will be the integral from negative 2 to 4 of f of t dt will be 27. All right, part D is capital F of 4. That's going to be the integral from, and we have to use capital F of x here. And x will be replaced with the 4, so you'll be the integral from 4 to 4 of f of t dt. Notice that the upper and the lower limits are the same, so the integral from 4 to 4 of f of t dt is 0. That's one of the properties for integrals that we talked about back in section 5.2. Again, refer to that video if necessary. And part E, a of 8. That means we need to use a of x right here, being the integral from negative 2 to x of f of t dt. So here we got the lower limit, negative 2. Our x will be replaced with 8, so it'll be from negative 2 to 8 of f of t dt. So we're going from negative 2, which is right over here, to 8. Then that's way over here. So now we got this area plus this area plus this area here. Two of them are above the x-axis, so that means that the area being 9 would be positive, plus this area right here that's in green is also above the x-axis, so it'll be positive 18, plus this 8, where we got right here, that's below the x-axis, so now that area will be negative 8. So that means here if I add 9 plus 18, that's 27. 27 plus negative 8 would be 19. So a of 8 would be the integral from negative 2 to 8 of f of t dt, and that final answer there would be 19. Okay. All right, next we'll look at the Fundamental Theorem of Calculus, and there are two parts that we will look at. Part 1 is going to be this. If f is continuous on the closed interval ab, then the area function, a of x, is equal to the integral from a to x of f of t dt for x greater than or equal to a and less than or equal to b is continuous on ab and differentiable on the open interval ab. The area function satisfies a prime of x equaling to f of x. So equivalently, a prime of x will be this. The derivative with respect to x of the integral from a to x of f of t dt equaling to f of x. And if you look at it, the derivative and the integral are inverses of each other. Okay? So you'll end up getting the f of t dt, or just f of t. And you replace the x with that t, so it would be f of x. And this means that the area function f is the antiderivative of f on the closed interval ab. And also, if u is a differentiable function, and this is something I added to these notes as well, then a prime of x is going to be equal to the derivative with respect to x of the integral from a to u of f of t dt, equaling to f of u times du dx. Okay. So here we just take this u up here, whatever that is, and usually it has to be an x up here as our upper limit, as you see here. But if it's something else here, and of course the a has to be some numerical value. A is a constant. That's your lower limit. But if u is something other than that x, then that means we'll take this u and replace it with f of u and then simplify it. And I do have an example of that you'll see shortly. All right, but let's look at example 2 and 3. Starting with example 2. Let's say I want to simplify this expression, the derivative with respect to x of the integral from 5 to x of 10x squared plus t plus 8 dt. Okay, notice my upper limit is x. And your x must be your upper limit for this fundamental theorem to be used. Okay? So all we have to do there is just simply replace this t with that x. So in this case here, that x will be put in place of t, so it'll be 10x squared plus the t is substituted with x, and then plus 8. And that's all there is to it. And that's all they ask for. So that derivative with respect to x of the integral from 5 to x of 10 t squared plus t plus 8, replacing each t with the x, you'll get 10x squared plus x plus 8. And then example 3 looks like this. The derivative with respect to x of the integral from x to 4 of the square root of t squared plus 1 dt. Well, first of all, my upper limit must be x. Here the x down here is a lower limit. So if I want this to be my upper limit, I just need to switch these two limits here. So if I do that, I must have a negative sign in front of the derivative with respect to x of the integral from, this time the 4 would be my lower limit and x would be the upper limit of the square root of t squared plus 1 dt. And then I'm going to bring this negative over. Now I can go ahead and replace, since I have x here, I can replace the t with this x here. So it would be the square root of x squared plus 1. And it'll actually be negative of the square root of x squared plus 1 for the derivative with respect to x of the integral from x to 4 of the square root of t squared plus 1. Okay. Now let's look at example 4 on the next page. In this case, notice that the x squared is my upper limit and not x. So I have the derivative with respect to x of the integral from 0 to x squared of dt divided by t squared plus 5. Okay. Now in this case here, here's what f of t is. Okay, and that's the 1, and that's actually 1 over t squared plus 5. That's what f of t is going to be. Now in this case here, I need to do a u substitution, so I need to let u be this upper limit, which is x squared. And take its derivative, du dx. And that's equal to 2x. Okay. So in this case, I need to follow this right here. That's going to be equal to f of u times du dx. So this will be equivalent to f of u times du dx. Now let's find out what f of u is going to be. So if f of t is going to be 1 over t squared plus 5 from here, then that means that f of u, I just replaced the t with the u, so it'll be 1 over u squared plus 5. So here's what I'm going to have, 1 over u squared plus 5 times du dx. Now, I let u equal to x squared, so I'm going to put this in terms of x. So I'm going to have 1 over, that u will be x squared, so I have x squared, but here I got this exponent of 2, so that's going to be squared, plus 5. And of course, this ends up being 1 over x squared, and I squared. Well, if I raise a power to a power, I multiplied my exponent, so it'll be x to the 4th plus 5. And I forgot something else here. That du dx, that needs to be multiplied by 2x. So if I do 1 times 2x, that's going to be 2x. So I have 2x divided by x to the 4th plus 5. Okay, because I let u be x squared, that meant du dx will be 2x. So I have 1 over u to the 5, that's going to be this part, times the du dx, that's 2x. So I end up with 2x divided by x to the 4th plus 5. Okay. All right, now, part 2 of the Fundamental Theorem of Calculus is going to be the main thing that we're going to be looking at in this video. So we're going to be applying part 2 of the Fundamental Theorem of Calculus. If f is continuous on the closed interval ab and capital F is any antiderivative of f on ab, then the integral from a to b of f of x dx will be this, capital F of b minus the capital F of a. Okay? We'll do the integration, but of course we're going to substitute our limits here. So it'll always be the upper limit, which is your f of b, minus your lower limit, f of a. And it is customary and convenient to denote the difference, f of b minus f of a, by this notation, f of x going from a to b. That's the shorthand. Okay. And here's pretty much the more detailed about this. The integral from a to b of f of x dx, that's going to be the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. And here's the shorthand notation again. So we're going to use this to take the integral, or find their definite integrals here. So in this case here, in example 5, the integral from 0 to 1 of 4x cubed plus 6 dx. And we're going to use the Fundamental Theorem of Calculus. Okay, so let's go ahead and integrate this. We got the integral of the sum. I can write this as a sum of their individual integrals here. So this will be the integral from 0 to 1 of 4x cubed plus the integral from 0 to 1. And I'm always leaving this off. It's got to be dx here. So let me write this out so I can include dx. So the integral from 0 to 1 of 4x cubed dx plus the integral of 6 dx. And this is from 0 to 1. Now that 4 is my coefficient for x cubed, I can pull that out of pull this out in front of the integral sign, so it'll be 4 times the integral from 0 to 1 of x cubed dx plus, and if I want to, I can pull the 6 out in front, so it'll be 6 times the integral from 0 to 1 of dx. Now, bring down the 4. The integral for x cubed, for x cubed, we use the power rule by increasing the power by 1. So it'll be x to the 4th. Divide that by your new exponent, which is 4, plus 6 times the integral of dx. We just tack on the x. Now this is going to be from 0 to 1. And if I simplify this a bit, let's divide out the 4's. So I have x to the 4th plus 6x. And this expression will be evaluated from 0 to 1. So now, using the fundamental theorem of calculus, we're going to do the upper limit minus the lower limit. My upper limit is 1, so it's going to be 1 raised to the 4th, just replacing the x with 1, plus 6 times x, which is 1, minus my lower limit, which is 0, so I replace every x with 0. So I have 0 to the 4th plus 6 times 0. And if I simplify this a bit, 1 to the 4th will be 1, plus 6 times 1 will be 6, minus, and I know what this is, 0 to the 4th, that's going to be 0, plus 6 times 0 is 0. 1 plus 6 is 7. 0 plus 0 is 0. 7 minus 0 ends up being 7. Okay, so in this case here, the integral from 0 to 1 of 4x cubed plus 6 dx gives me a value of 7. And that represents the area under the curve bounded by the graph of this function and the x-axis from 0 to 1. All right, problem number 6, or example 6 on the next page. Here we want to evaluate the following integral using the fundamental theorem of calculus. So here we got the integral from 3 to 6 of 2x squared plus 7x dx. Okay, well, I got the integral of the sum. I can write that as the sum of their individual integrals here. So I'll write this as the integral from 3 to 6 of 2x squared dx plus the integral from 3 to 6 of 7x dx. And I can pull their coefficients out in front of the integral sign. This 2 can go out in front as 2 times the integral of 3 from 3 to 6 of x squared dx. Plus, pull the 7 out in front, that'll be 7 times the integral from 3 to 6 of x dx. And then we can go ahead and do the integration here. Bring down the 2. The integral of x squared, I'll do that using the power rule by increasing the power by 1, dividing it by that exponent of 3, and then plus 7 times integral of x dx. I can use the power rule again by increasing the power by 1, dividing by that new power. And this is from 3 to 6. And I forgot to mention that with these definite integrals, we don't use plus c, because we have our limits, our upper limit and lower limit. So the plus c is not included. Now if I simplify this, this will be 2/3 x cubed plus 7 over 2 x squared. And that's going to be from 3 to 6. And then next we just substitute by doing the upper limit minus the lower limit. So starting with the upper limit, I have 2/3 times x, which is 6, and that's going to be cubed, plus 7 halves x again, that would be 6, and that's going to be squared, minus my lower limit, 2/3 times x, which is 3, and that's cube, plus 7/2 times x, which is 3, and that's squared. And I'm going to have to do this on the calculator here, so that way you can see how I'm going to simplify this. Let's start with the upper limit. So that 2/3, I'm going to do this as 2 divided by 3, close parentheses, times 6, and that's going to be raised to the third, plus, that 7/2 will be 7 divided by 2, times 6, and that's squared. This part would give me the 270. So here I'm going to have 270 minus, now the lower limit, I'm going to do 2/3, so this will be parentheses 2 divided by 3, times 3, and that's going to be cubed, plus, and I'm putting 7/2 in parentheses, so that's 7 divided by 2 times 3, and that's squared. This gives me 49.5. Now if I do 270 minus 49.5, 270 minus 49.5, that'll give me 220.5 as the final answer. However, I might want this as a fraction. So for that 220.5, I'm going to press the math key and then number 1 for fraction. And that will give you 441/2. So the integral from 3 to 6 of 2x squared plus 7x dx ends up being, as a fraction, 441 halves. That represents the area of the curve, the area that's bounded by the graph of this function, and the x-axis from 3 to 6. All right, example 7 looks like this. Here we got the integral from 1 to 4 of 6x plus the square root of x dx. Okay. And here's what I'm going to do here. The square root of x in its equivalent exponential form is going to be 1/2. So I'm going to write this as the integral from 1 to 4 of 6x plus x raised to the 1/2 dx. Now I'm going to use a combination of the sum rule along with the constant multiple rule. For the 6x, I'll pull the 6 out in front, so it'll be 6 times the integral from 1 to 4 of x dx plus the integral from 1 to 4 of x to the 1/2 dx. So for the 6, the integral of x dx, we increase the power by 1, so it'll be x to the 2nd divided by 2, plus, and for the integral of x to the 1/2 dx, we increase the power by 1. So this will be x to the 1 plus 1/2, and you can do this in the calculator. 1 plus 1 divided by 2, and then press the math key and number 1 for fraction. That would give you 3/2. So it'll be x to the 3/2 divided by my new exponent of 3/2. And this is, in this case, going to be from 1 to 4. So if I divide 2 into this 6, that's going to go 3 times. So that means I'm going to have 3x squared. Plus, now, the reciprocal of 3/2 would be 2/3. So this would be 2/3 x to the 3/2. And that's going to be from 1 to 4. I apologize for trying to put all of this in a little space that I have. Okay, now we do the upper limit minus the lower limit. My upper limit is 4, so I have 3 times 4 squared plus 2/3 times the x, which is 4, to the 3 halves, minus my lower limit, that'd be 3 times 1 squared plus 2/3 times 1 to the 3 halves. Let's see if we can do all of this in the calculator. Let's start with that lower limit. I'm going to do left parentheses 3 times 4, and that's squared, plus, and in parentheses 2 divided by 3, close parentheses, times 4, press the hat key for the exponent, 3 divided by 2. Then I'm going to close that parentheses. So the upper limit will have a value of 53.333, but I'm going to press the math key and select number 1 for fraction. That would be 160/3. And then minus our lower limit. Evaluate that. It will be, and I'm going to say left parentheses, 3 times 1, and that's squared, plus, and then put 2/3 in parentheses, that's 2 divided by 3, times 1, and then the hat key, 3 divided by 2. Close parentheses. Okay, that's a decimal. Press the math key and then number 1 for fraction. This will be 11/3. So now I got 160/3 minus 11/3. Well, my denominators are the same. I can subtract the numerator, so this will end up being 149/3. So the integral from 1 to 4 of 6x plus the square root of x dx will be 149/3. Okay. All right, example 8. Let's say I want to use the fundamental theorem of calculus to evaluate the following definite integral. And in this case, we got the integral from -2 to 5 of 5x squared plus 2 dx. Okay. And I'll use a combination of the sum rule and the constant multiple rule. For that 5x squared, I'll pull the 5 out in front, so it'll be 5 times the integral from -2 to 5 of x squared dx, plus, I can pull the 2 out in front, so it'll be the integral, 2 times the integral from -2 to 5 of dx. And then just do the integration here. To integrate x squared dx, we just increase the power by 1. Divide that by the new exponent of 3. Here I'm using the power rule for integration. And then plus, bring over the 2. Integral of dx would just be x. And all of this is from -2 to 5. So if I rewrite this a bit, this will be 5/3 x cubed plus 2x. And that integral will be from -2 to 5. Now we do the upper limit minus the lower limit. Replace this x with the 5, so this will be 5/3 times 5 cubed plus 2 times x, which is 5, minus my lower limit, 5/3 times, and this will be -2 raised to the 3rd plus 2 times -2. So let's evaluate the upper limit, what that upper limit is. Left parentheses, and then I'm going to do 5/3 in parentheses, that's 5 divided by 3 times 5, the hat key and then cube it, use your right arrow to get out of it, plus 2 times 5, close parentheses. And I'm going to write this as a improper fraction by pressing the math key and selecting number 1 for fraction. This will be 655 over 3 for the upper limit. And then minus my lower limit. Let's evaluate that. Let's do left parentheses, and then in parentheses, 5 divided by 3, minus, and this will be negative 2, hat key, to the third, plus 2 times negative 2, close parentheses. Now, if I press the math key and then number 1 for fraction, that would be, I'm doing something wrong here. Let me do this. If I put that negative 2 in parentheses here, I'll do it over. Left parentheses and then left parentheses, 5 divided by 3 times negative 2 in parentheses, and then that's going to be cubed, plus 2, left parentheses, negative 2, close parentheses, and then close it again. Okay, so now press the math key and number 1 for fraction. This will be negative 52 over 3. So I got 655 over 3 minus negative 52 over 3. And in this case, I can treat this as I can treat this as 655 thirds plus 52 over 3. That would give me 707 over 3. And I'll leave that as an improper fraction. That will be the integral from negative 2 to 5 of 5x squared plus 2 dx. Okay. All right, example 9 looks like this. The integral from 1/2 to 1 of x to the negative third minus 6 dx. Again, using the Fundamental Theorem of Calculus. Well, I'll go ahead and break this up as the integral from 1/2 to 1 of x to the negative third dx minus, and I'll pull the 6 out in front, times the integral from 1/2 to 1 of dx. All right, so now, using the power rule for each one of these. In this case here, we increase the power by 1. So it'd be x to the negative 3 plus 1, that's negative 2, divided by negative 2, then minus, bring down this 6, integral of dx would just be x. And this is from 1/2 to 1. And I'm also going to write this as using positive exponents. So I'll bring the negative out in front. The 1 will be in the numerator. The 2 remains in the denominator, but x to the negative 2 goes down in that denominator as a positive exponent. So it'll be negative 1 over 2x squared minus 6x. And that's going to be from 1/2 to 1. Okay, and I'm going to continue this over here by doing the upper limit minus the lower limit. All right, so my upper limit is a 1, so it'll be negative 1 over 2 times 1 squared minus 6 times 1. Then minus the lower limit is 1/2, so it'll be negative 1 times 2 times a half, and that's going to be squared minus 6 times 1/2. This equal sign, equal sign. Let's see what we can do with this here. Okay, negative 1 divided by, and in parentheses, 2 times, not negative 1, it's just 1. Left parentheses, well, it's negative 1 because of the negative sign in front, so it'll be negative 1 divided by parentheses 2 times 1, and that's squared, close parentheses, minus 6 times 1. Then I'm going to close the parentheses. That would be negative 6.5, but as a fraction, I'm going to say negative 13 over 2. And then minus. Okay, now for this one, I'm going to do left parentheses and then negative 1 divided by, and in parentheses, 2 times, I'm going to treat 1/2 as 0.5 and then square it. That's what I'm going to do here. And then minus 6 times 0.5. I'll treat that as 1/2 as well. And that's going to give me negative 5. So if I do this, negative 13 divided by 2 for negative 13 halves, minus negative 5, then press the math key and then number 1 for fraction, this will give me negative 3 halves. Okay. In this case, I treated 1/2 as a decimal, 0.5. So in this case here, the integral from 1/2 to 1 of x to the negative 3 minus 6 dx will be negative 3 halves. All right, number 10. Number 10. Let's say I want to evaluate the following integral using the fundamental theorem of calculus again. So here we got from the integral from 3 to 13 of 3 minus x times x minus 13 dx. Okay, and let's say I want to find out what that integral is going to be. I need to go ahead and multiply this out using the FOIL method. So this will be the integral from 3 to 13 of this. First will be 3 times x, or 3x. The outer, 3 times the minus 13, will be minus 39. The inner, minus x times x, will be minus x squared. Then the last times the last, minus x times the minus 13 will be a plus 13x dx. And I'm going to simplify this and write this in descending power. So I have the integral from negative 3 to 13 of, and I'm going to put the negative x squared in front. 3x and 13x will be plus 16x minus 39. And then include dx. Okay. And then I'm going to integrate each piece and then use the constant multiple rule whenever necessary. In this case, I'll pull the negative out in front, so it'll be negative the integral from 3 to 13 of x squared dx. Plus, I'll pull the 16 out in front, so it'll be 16 times the integral of x dx, minus, and then pull the 39 out in front, so it'll be 39 times the integral of dx. And now we can go ahead and integrate each part. Bring this negative down. Integral of x squared dx, we increase the power by 1, so it'll be x cubed over 3, plus 16 times. Integral of x dx, we increase the power by 1 as well, so it'll be x squared over 2, minus 39. Integral of dx will be x. And all of this is going to be from 3 to 13. All right, so now we got negative, and I'll write this as negative 1/3 x cubed plus, divide 2 into 16. That's going to go 8 times. So I have 8x squared, and then minus 39x. And this will be from negative, not from negative, from 3 to 13. So now we just find the upper limit minus the lower limit. I'll continue this over here on this side. My upper limit is 13, so I have negative 1/3 times 13 cube plus 8 times x, which is 13, and that's square, minus 39 times 13. And then minus my lower limit, which is 3, so it'll be negative 1/3 times 3 cube plus 8 times 3 square minus 39 times 3. And all of this is going to be, I'm going to have to punch all of this in the calculator. For this upper limit, let's start with that. And then left parentheses, negative 1 divided by 3 for negative 1/3 times 13, hat key, and then cube it. Then plus 8 times 13 square minus 39 times 13, close parentheses. Let's see what we get. Okay, now that's a decimal. I need that as a fraction, so math number 1 for fraction. This will be 338 over 3 for this part. And then minus this lower limit. So here we'll do left parentheses, and then we'll do left parentheses again for the negative 1/3. So it'll be negative 1 divided by 3 and close that parentheses times 3, hat key and cube it, plus 8 times 3, and that's squared, minus 39 times 3, close parentheses. So this is a minus a negative 54. All right, so I can type this in the calculator as 338. Well, let me do this. In parentheses, 338 divided by 3, close parentheses, minus a negative 54. Hit your math key and then press number 1 for fraction. You'll get 500 over 3. 500 over 3. So the integral from 3 to 13 of 3 minus x times x minus 13 dx will be 500 over 3. Okay. All right, example 11 has a trig function in it. And this is where you have to know your integrals for trigonometric functions. Here we got the integral from 0 to pi thirds of 10 times the secant square of x dx. Well, notice that the 10 is a constant. I can pull that constant out in front. So that means I'm going to have 10 times the integral from 0 to pi thirds of secant square of x dx. So let me bring down the 10. Now, the integral of secant square of x, if you recall, is tangent of x. And this is going to be from 0 to pi thirds. Might need to refer back to a video for section 4.9, when we talked about antiderivatives. And one of them was for those 6 trigonometric functions. So be familiar with those integrals for your 6 trigonometric functions. The integral for the secant square of x will be the tangent of x. And we're going from 0 to pi thirds. All right, so now let me bring down the 10. I'm just going to focus on the tangent of x. Upper limit minus the lower limit. So here I have tangent of the upper limit, which is pi thirds, minus the tangent of the lower limit, which is 0. Well, tangent of pi over 3, you just have to refer back to your unit circle. Tangent of pi thirds is like sine over the cosine, sine of pi thirds over the cosine of pi thirds. This will end up being the square root of 3. Minus the tangent of 0 is 0. Well, square root of 3 minus 0 is the square root of 3 times 10. That'll be 10 square root of 3 as the final answer. So the integral from 0 to pi thirds of 10 times secant squared of x dx would be 10 square root of 3. Okay. Example 12. Let's say we got the integral from 1 to 8 of 6 over t dt. Integral from 1 to 8 of 6 over t dt. All right, that 6 is a constant, so I'm going to pull the 6 out in front, and that'll be multiplied by the integral from 1 to 8 of 1 over t dt. Okay. Back in section 4.9, we talked about the integral of 1 over x dx. That's equal to the natural log of the absolute value of x. So the integral for 1 over t dt, let me bring the 6 over, this will be the natural log of the absolute value of t. And this will be from 1 to 8. Okay? So do be familiar with those integrals, especially for e to the x and for the natural log as well. Or 1 over t dt, I should say. Now, upper limit minus the lower limit here. So this will be 6 times, I'm just going to focus on just the ln of t. So here I got 8, so it'll be ln of the absolute value of 8 minus ln of the absolute value of 1. Okay. By the way, this is the absolute value right here. And of course, the absolute value is always going to be positive. So if I take the absolute value of 8, it'll be 8. So I have ln of 8 inside the parentheses minus ln of the absolute value of 1 is 1. But I do know something about the the natural log of 1. Natural log of 1, that's automatically going to be 0. Minus ln of 8, from ln of 8 would be ln of 8, so it'll be 6 times the natural log of 8. And I think you can go no further than that. That's what they want as an answer. Because they might want something like this. ln of 8 to the 6 using the power rule, and then you'll simplify what ln of 8 to the 6 is, or just simplify what 8 to the 6 is. Or they might want this ln of, and if you do 8 to the 6, that would be 262,144. Okay. But I think they want 6 ln of 8 as the final answer for the integral from 1 to 8 of 6 over t dt. Okay, example 13. Here we got the integral from 27 to 64 of the cube root of y dy. Well, let's write the cube root of y in exponential form. So it'll be y to the 1/3 dy. And then we'll just go ahead and integrate y to the 1/3 dy as adding 1, increasing the power by 1. So it'll be y to the 1/3 plus 1. Then math, and then number 1 for fraction. That would give you 4/3. So it'll be y to the 4/3 divided by that new exponent of 4/3. All right, and then the reciprocal of 4/3 will be 3/4. By the way, this will be from 27 to 64. So it'll be 3/4 y to the 4/3, and this will be from 27 to 64. And I'm just going to focus on the y to the 4/3. So I'm going to pull the 3/4 out and just do this. Upper limit minus the lower limit. So this will be 64 to the 4/3 minus the lower limit, 27. to the 4/3. Bring the 3/4 down. Let's see here. If I do 64 to the 4/3 in the calculator, that'd be 64, then the half key 4 divided by 3. That would be 256 minus, and then 27 raised to the 4/3. 27 half key 4 divided by 3, that's 81. And then if I do 256 minus 81, that would be 175. So I have 3/4 times 175. And this will have to be 175 over 1 times 3/4. This will give me 525 in the numerator and 4 in the denominator. So the integral from 27 to 64, the cube root of y dy will be 525 over 4. Okay. All right, number 14. Here I want to evaluate the following definite integral used in the fundamental theorem of calculus. Here we got the integral, 1/4 times the integral from 0 to the natural log of 5 of e to the x dx. Well, notice they did you a favor by pulling the 1/4 already on the outside. What's the integral of e to the x dx? That's the simplest integral to take. E to the x. And this will be from 0 to the natural log of 5. So now I got 1/4. Now, the upper limit is L in the 5, so I'll replace the x with L in the 5. So this will be e to the natural log of 5 minus the lower limit, which is 0, so it'll be e to the 0. So I have 1/4 times. Now, there's a rule that states, or a property for natural logarithms and the natural base e, that clearly states if you have e to the ln of whatever your exponent is, or whatever this is, it's going to be x, because e and ln are inverses of each other. So e to the ln of whatever is whatever. So e to the ln of 5 would just be 5 minus e to the 0 is a non-zero number to a power of 0. That's going to be 1. And then 5 minus 1 would be 4. So 1/4 of 4 ends up being 1. Okay. So that's 1/4 times the integral from 0 to the natural log of 5 of e to the x dx will be equal to 1. All right, and finally, example 15. Let's say I want to evaluate the following definite integral, again, using the fundamental theorem of calculus. Here I got the integral from 1 to 2 of z squared plus 3 over z dz. Well, let's do this. Bring down the integral from 1 to 2, and I'm going to divide each of these terms by this monomial of z, which I can do. So it'd be z squared divided by the z plus 3 divided by z dz. Now if I simplify this, z squared divided by z will just leave me with z plus 3 over z dz. Now we're going to break this apart and use the sum rule and the constant multiple rule together. So here I got the integral from 1 to 2 of z dz plus, and if I pull that 3 out in front, so I have 3 times the integral from 1 to 2 of 1 over z dz. Now let's do some integration here for each one of these. If I integrate z dz, this will be increasing the power by 1, so it'll be z squared over 2, plus 3 times the integral of 1 over z dz will just be the natural log of the absolute value of z. And this will be from 1 to 2. Keep in mind, integral of 1 over z dz or 1 over x dx will be the natural log. Now we're going to do the upper limit minus the lower limit. All right, so let's start with the upper limit of 2. This will be 2 squared over 2 plus 3 ln of, well, if I'm replace the x with 2, the z with 2, it'll be the absolute value of 2, which is 2. And then minus my lower limit. Z will be 1, so it'll be 1 squared over 2 plus 3 ln of absolute value of 1 will be 1. Now let's do some simplifying here. If you square the 2, that's going to be 4. 4 divided by 2 is 2. So I have 2 plus 3 ln of 2 minus, let's see, 1 squared will be 1 divided by 2. That's going to be 1/2. ln of 1 is 0 times 3 is 0. Okay, don't believe me, use your calculator. Press the ln key and type in the number 1. You'll see that it will equal to 0. All right, so now we got 2 plus 3 ln of 2 minus 1/2. 1/2 plus 0, that's 1/2. Now let's do 2 minus 1/2 in the calculator. And as a fraction, you'll get 3/2. So 2 minus 1/2 would be 3/2. Plus 3 ln of 2. And that would be as far as I would go with that problem here, or what my math lab would want as an answer, because they might want you to simplify this by making that 3 an exponent for the 2, which might be 3/2 plus ln of 2 cubed, or 3/2 plus ln of 8. But I'm sure they'll want this as an answer. Okay? All right, so that does complete this video on section 5.3 dealing with the Fundamental Theorem of Calculus. Feel free to reach out to me if you have any questions about anything that was presented in this video or any of the homework problems that are in my math lab.